Hi, I'm Yun-Sheng from Academia Sinica, Taiwan. In this talk, I will introduce our recent project called Snapshot-Consistent Flash Translation Layer, or SCFTL for short. This is a joint work with my colleagues at Academia Sinica. So what is SCFTL? SCFTL is a flash translation layer with a simple and useful specification. The specification is called a Snapshot-Consistent Disk Model. It guarantees snapshot consistency, which, in a nutshell, allows users to create a disk snapshot simply by flashing the disk. If a crash occurs, SCFTL is guaranteed to roll back the disk state to the previous snapshot. Moreover, the specification exposes the standard read-write flash disk interface that users are familiar with. SCFTL also has a good performance by exploiting the out-of-place update nature of FTLs and using an efficient checkpointing algorithm. SCFTL is able to guarantee snapshot consistency while maintaining the good performance. Finally, to increase our confidence that SCFTL actually guarantees snapshot consistency, and to make sure the good performance does not come from an incorrect implementation, we have formally verified our implementation of SCFTL against its specification. To understand why SCFTL is useful, let's begin with an overview of the storage stack. Broadly speaking, the storage stack starts from the application layer, goes through the file system, and eventually reaches the underlying disk. The storage stack should be crash-safe, meaning that they don't have unexpected behavior even in the face of a crash. One interesting observation about the storage stack is that oftentimes the correctness and performance of upper layers are determined by the guarantee provided by their lower layers. However, because of the optimization lower layers adopt, upper layers often have to make minimal assumptions about their lower layers. For example, file systems usually assume the underlying disk follows the asynchronous disk model, which ensures only the disk write before the last flush are durable. But for writes after the last flush, each of them may or may not survive across a crash. The consequence is that a system call may have partial effect on the disk after a crash, resulting in file system inconsistency. To cope with this issue, file systems usually use a crash recovery mechanism, such as a write-ahead log, to protect themselves against crashes. However, it is often hard to get it right because the crash behavior is quite complicated. Recent research has discovered bugs in widely used file systems, such as ESD4 and BTIFS, and bugs in file systems are still being reported. As a result, a significant amount of research effort is devoted to eliminating bugs in file systems with formal verification. Besides, crash recovery mechanisms also incur performance overhead because data are written twice and expensive write barriers are required to enforce the write order, for example, between the journaled data and the commit record. There are, of course, some optimization to reduce the overhead. However, they often also compromise the crash guarantee file system are able to provide. For instance, ESD4 by default journals only metadata update and bypasses the log for data updates. This optimization reduces the amount of data written to the log, but it also breaks the order between the two kinds of updates on a crash. This behavior, in turn, results in many crash vulnerabilities in widely used applications and ACID violation in database systems, as discovered by recent research. In this work, we adopt an alternative approach to the development of a crash-safe storage stack, which is to provide a stronger crash guarantee at a disk level. This approach is similar to prior work, Abstration and BarrierFS, which propose order-preserving disk models that preserve the order of disk operation across crashes. With the order-preserving disk model, we can remove some flushes that are used to enforce ordering constraint to achieve better performance. Our proposed snapshot-consistent disk model provides an even stronger crash guarantee, as shown with the following example. In the example, we have a disk with only 3 sectors. Before encountering a crash, the disk received a flush followed by 2 write. We show the allowed crash behavior of each disk model on the right-hand side. For the asynchronous disk model, each write may or may not survive across a crash. So there are at most 2 to the power n possible post-crash states. For the order-preserving disk model, writes are not allowed to be reordered. So there are at most n plus 1 post-crash states. For the snapshot-consistent disk model we propose in this work, the disk state is guaranteed to roll back to the state right before the last flush. So there can be only 1 possible post-crash state. Moreover, we can easily model this behavior with 2 arrays. The first array, volatile, represents the disk state observable to the users, and the second array, stable, captures the disk state right before the last flush. The flush operations copy the contents of the volatile array to the stable array. The write and read operation only access the volatile array. The recovery procedure does the opposite of flush. It copies the contents of stable array back to the volatile array. Please see the paper if you are interested in the formal specification. The major benefit of snapshot consistency is that it ensures the atomicity of multiple disk write between 2 consecutive flushes. With snapshot consistency, file system can simply call a flush to commit a transaction. Also, it improves the system performance because data are only written once and no write barriers are required. So far, we have covered the specification of SCFTL and why the specification can be useful to the upper layers. Next, I will talk about the design of SCFTL. The main goal of SCFTL is to, obviously, guarantee snapshot consistency, but we also wanted to maintain a good performance. To this end, SCFTL employs 2 main techniques, checkpointing and two-phase garbage collection. Checkpointing is used to remember the disk state right before the last flush, and two-phase garbage collection prevents an issue called premature erasure. Before we dive into the detail, I will briefly describe some flash memory and FTL basics. Flash memory has a few intrinsic device characteristics. One notable constraint that should be followed is that a page has to be erased before being written to. Moreover, the basic unit for write is a page, but the basic unit for erase is a block, which contains multiple pages. Therefore, it will be inefficient if we erase the entire block whenever we write a page to it. To free users from this undesired characteristic, most flash disks come with a flash translation layer, which implements the disk interface using flash operations and performs out-of-place update with a logical to physical table, or L2P for short. Below, we will see an example of how an FTL performs out-of-place update, and more importantly, why this feature is useful for SCFTL to guarantee snapshot consistency. In the example, the FTL maintains an L2P table in memory and stores host data in flash. To handle a write request, the FTL finds a free page and put the host data there. Then it updates the L2P entry to the page just written. The key observation is that all the old data remain intact at their previous locations. So if SCFTL can remember where the old data are, then it can roll back to the previous disk state after recovery. To realize this concept, SCFTL keeps track of the locations of the old data with another L2P table called stable L2P. The stable L2P reflects the disk state right before the last flush, so that after recovery, SCFTL can roll back the disk state to the previous snapshot. To distinguish the two L2Ps, we will call the in-memory one the volatile L2P. When SCFTL receives a write operation, it only modifies the volatile L2P, but not a stable L2P. On the flush operation, SCFTL copies the volatile L2P to the stable L2P. The next question is, how to efficiently maintain the stable L2P. In SCFTL, the stable L2P is stored as a full image in flash memory, and we call this process full checkpointing. But storing the entire L2P is an expensive operation. So SCFTL also creates delta checkpoint to record only the L2P differences. Whenever the volatile L2P table is modified, a delta pair, which consists of a logical address and a physical address, is added to the delta buffer. When the buffer is full, SCFTL stores the buffer pairs along with the tentative flag in a page located in the reserved region. When SCFTL receives a flush, it also stores the buffer pairs in flash. But this time, the page is tagged with a committee flag. A committee flag activates all previous delta pairs, meaning that all delta pairs prior to the committee tag are all considered committed. For instance, in the example, the first 3 pages of delta pairs are all committed, while the last page of delta pairs are not. The stable L2P is represented by using an in-flash L2P as a base image, and sequentially applying all committed delta pairs. As we will see later in the verification part, we will need this property to connect our implementation to our specification. But this is not the end of the story, because even if we maintain the stable L2P to keep track of where the old data are, the garbage collector may still delete the old data, and in this case, SCFTL will not be able to roll back to the previous snapshot. To understand why this can happen, let's see how the standard GC works. The standard GC begins with choosing a victim block, then it relocates valid data in a victim block to another block, and finally, erase the victim block, and the block can be reused thereafter. The problem is that the garbage collector only relocates data referred by the volatile L2P, but for those referred by the stable L2P, they may be deleted prematurely. A naive solution is to also relocate data referred by the stable L2P, but this may incur performance and memory overhead, and may also complicate the recovery procedure. To address this issue, SCFTL uses a simple protocol called two-phase garbage collection, or 2PGC for short. 2PGC simply decouples the standard GC into 2 phases, the relocation phase and the erasure phase. The key difference between 2PGC and standard GC is that in 2PGC, the erasure phase is delayed until a flush is invoked. The reason 2PGC works is that after a flush, the stable L2P is the same as the volatile L2P, and therefore, the old data are no longer referred by the stable L2P after a flush. Now that we have the specification of SCFTL, which involve 2 arrays, and we also have an implementation that is much more sophisticated than the specification. To prove that the implementation is correct with respect to the specification, we need to connect the 2 of them with abstraction relations. Intuitively, abstraction relations capture how the state in the implementation is interpreted as a state in the specification. Besides, we often need some representation invariant to describe properties that should be satisfied by various data structures in an implementation state. Below, we will see a few examples of the abstraction relation and representation invariants required to verify SCFTL. For instance, a part of our abstraction relation says that the volatile array in the specification is implemented by looking up physical addresses in the in-memory L2P and indexing the data region with the addresses to find the content. It also says that the stable array is implemented similarly to the volatile array, except this time the physical addresses are taken from the stable L2P, which, as mentioned earlier, is represented by a committee in-flash L2P and all committee delta pairs. For the representation invariant, One of them says that at least one in-flash L2P is committed. And another one says that starting with the committed in-flash L2P and applying all delta pairs in the delta region and in the delta buffer should yield the in-memory L2P. With proper abstraction relation and representation invariant, we then use the symbolic executor servo and the SNT solver Z3 to prove that the implementation and the specification establish a forward simulation. More specifically, we prove that in the absence of crashes, every operation should preserve the abstraction relation AR and the representation invariant RA. But if a crash occurs, the relationship can deteriorate to their weaker versions, CR and CI. CR and CI should describe only the properties about flash state, because a crash would tear down the in-memory content. Besides, we should design CR and CI to be weak enough to hold even with crash reordering, but strong enough to allow a successful recovery. To account for crashes during recovery should be idempotent, meaning that CR and CI should be preserved if a crash occurs during recovery. Finally, the relationship should restore to AR and RI on a successful recovery. To evaluate SCFTL, we use the Linux Lite NVM module to host our SCFTL and the FEMU emulator to emulate flash memory. We use a disk workload that issues random write requests and invokes a flash for every given number of writes. To identify the performance overhead due to snapshot consistency, we compared SCFTL with another FTL whose design is similar to SCFTL, except the FTL follows the asynchronous disk model. So it doesn't need to do checkpointing, nor does it follow the 2PGC protocol. Evaluation shows that when the workload does not flush the disk too frequently, SCFTL is almost as efficient as the FTL implementing the asynchronous disk model. But when the workload frequently flushes the disk, SCFTL does not perform very well because flushes are more expensive in SCFTL. This observation suggests an important guideline for building system and application on top of SCFTL, which is to reduce the flush frequency to extract more benefit from SCFTL. To understand the usefulness of SCFTL, we modified the XV6 file system to support a standard optimization called group commit and to exploit the strong crash guarantee granted by SCFTL. Then we used the file system benchmark to evaluate this modification. By changing less than 30 lines of code, XV6 with group commit on SCFTL outperformed XV6 with logging on conventional FTLs by 3 to 30 times. Finally, we compared XV6 on SCFTL with the state-of-the-art setting, the EST4 file system on the pblk FTL. Evaluation shows that XV6 on SCFTL is at worst 2 times slower than EST4 on pblk. Moreover, XV6 on SCFTL has a stronger crash guarantee than that of EST4 on pblk. In conclusion, SCFTL provides a strong crash guarantee while maintaining a good performance, and its implementation is formally verified against its specification. We demonstrate that starting at a lower level of abstraction can make verifying crash safety easier, while still resulting in an efficient system. As for future work, we plan to build an efficient storage stack by exploiting the benefit brought by SCFTL, and to extend SCFTL with common FTL optimization, such as wear leveling and hardcode data separation. Thank you for listening.